from the Università di Pisa. We're going to talk about bounded cohomology and combinatorial volume forms.
Okay, thank you very much for the invitation. It's my first time here in Cambridge, and it looks wonderful so far. So today I would like to speak about bounded cohomology and some applications of coarse geometry to the study of bounded cohomology. So I would like to convince you that there is a deep relationship between coarse geometry and bounded cohomology. Okay, so let's start. So let me begin with the definition. So for a group G, we have the usual homogeneous resolution of R, which is just given by functions from G to the n plus 1 to R, with the usual differential on cochains. And we take invariant cochains. Today I will work only with trivial real coefficients, so I will not speak about integral coefficients, neither of more complicated modular space coefficient spaces. And so we take invariant cochains, and the cohomology of the group is just the homology of the complex of invariant cochains. What is bounded cohomology? It's just what the name suggests. So instead of taking all cochains, we just take bounded cochains with respect to this L infinity norm, which is just the norm of the supremum. So we take cochains that are uniformly bounded on n plus 1 tuples of elements of G. And bounded invariant cochains are a subcomplex of all invariant cochains. And so we can take the cohomology of this complex, and this is just the bounded cohomology of G. So these are the standard and very natural definitions. One can do the same thing for topological spaces. Okay, before let me just emphasize that there is also a semi-norm on bounded cohomology. You take a class, and the semi-norm of the class is just the infimum of the semi-norms over all the possible representatives. So over all possible bounded cocycles representing the class. Of course, it is a semi-norm and maybe not a norm, because a non-trivial co-class may have representatives of arbitrarily small norm, and this will be the central topic of this talk, by the way. Okay, for topological spaces we can do basically the same thing. Now the norm of a singular cochain is just the supremum of the values that the cochain takes over singular simplices. And again, we can take just the complex of bounded singular cochains, and the cohomology of this complex is the bounded cohomology of the topological space. Okay. Let me emphasize here that the L infinity norm on singular cochains arises as the dual of an L1 norm on singular chains. And the L1 norm is just the ones which evaluates as the sum of the absolute values of the coefficients in a finite sum of singular simplices. Okay, there is the classical theorem asserting that the bounded cohomology of an aspherical space is canonically isomorphic to the ordinary singular cohomology of the fundamental group of the space, carries over to the bounded context, basically with a similar proof. Indeed, in the bounded context, this equality is true even without asphericity of the space. This is a very deep theorem by Gromov, with another proof by Ivanov, but we will not need this theorem today, so we can stick to aspherical spaces. And let me emphasize that these isomorphisms are isometric with respect to the L infinity norm I have just introduced. So it is the same thing to compute the bounded cohomology of the group or computing the bounded cohomology of an spherical model for the group. Okay, this is the background. And first of all, one wants to compare the bounded cohomology, which is a bit more exotic than ordinary cohomology, to ordinary cohomology. There is a map, because bounded cochains, of course, can be mapped into ordinary cochains. And this is, of course, a chain map, which induces a map on cohomology. The surjectivity of this map amounts to recognizing which classes can be represented by bounded cocycles. And the injectivity of this map boils down to understanding if a bounded class which has a possibly unbounded primitive also has a bounded primitive. And today we will concentrate mostly on this second aspect of the comparison map. So on the injectivity or on the failing of injectivity of this comparison map. The kernel of the comparison map is denoted by this symbol, where E stands for exact. This is the exact bounded cohomology, meaning that elements here are just those classes which admit a primitive, possibly unbounded primitive. Okay, this is why they are called exact coclasses. Okay, bounded cohomology is related to coarse geometry and quasification, and this is one reason why it is related. There are many reasons, of course, but this is one reason. So if we take an exact bounded cohomology class, by definition, it admits a primitive. It is the coboundary of some possibly unbounded cochain. And an unbounded cochain F, whose differential is bounded, is what is called a quasi-cocycle. Okay? Because its coboundary is not 0, so it's not a cocycle, but it is close to be 0 because it's bounded. So it's called a quasi-cocycle. And the defect of the quasi-cocycle measures the failing of being a cocycle, and it is just the L infinity norm of the differential. We define the space of quasi-cocycle over Z just by taking what I called quasi-cocycles. So cochains whose differential is bounded. Basically, by definition, let me emphasize again that every exact bounded coclass comes from a quasi-cocycle. It is the differential of a quasi-cocycle, basically by definition. And in the one-dimensional case, so when studying two-dimensional bounded cohomology, so studying two-dimensional bounded cohomology, when studying exact classes, boils down to studying one quasi-cocycles. And one quasi-cocycles are very well known as quasimorphisms, because if we switch from the homogeneous resolution of G to the not homogeneous one, the bar resolution, then a quasimorphism is just something which is close to a one cocycle, which is just a real homomorphism. So it is a quasi-real homomorphism, which is usually called a quasimorphism. So it is a map which has this defect K. So it is not a homomorphism, but it is close to a homomorphism. And quasimorphisms, there is a huge literature on quasimorphisms. And for example, the free group admits a lot of quasimorphisms, which were constructed by many people. Here are just probably the first ones who published something on this topic. And by exhibiting a lot of quasimorphisms, one can prove that the dimension of the bounded cohomology of the free group is infinite. This result has been generalized in many directions. Let me just go to the end of the story, so far at least. And so a group is acylindrically hyperbolic. This is a definition due to Dennis Ozin, I guess. If it admits a non-elementary acylindrical action on a Gromov hyperbolic space. I'm not interested in the very definition of this class of groups. Suffices to say that it is a huge class of groups, which includes non-elementary relatively hyperbolic groups, most mapping class groups, and most subgroups of mapping class groups, out Fn, and one relator groups with at least 3 generators. So it's a huge class of somewhat negatively curved groups. Okay? And it can be shown that the second bounded cohomology of any of these groups is infinite dimensional. There are several ways to prove this. For example, Besvina, Bromberg, and Fujiwara proved this by constructing a lot of quasi-morphisms. In fact, they proved this statement for very general coefficient modules. Another way to prove this statement is due to Hall and Ozin, and it is very similar to what we will do today in this talk. It is first use the fact that the bounded cohomology of the free group is infinite dimensional, and then try to reduce this statement from acylindrically hyperbolic groups to free groups, using the fact that any acylindrical hyperbolic group contains a hyperbolically embedded free group. This will be clear in what I'm saying, in what follows. Okay, we are mainly interested in going from dimension 2 to dimension 3, and maybe higher. Higher it's an open problem, basically. So today we'll stick to dimension 3. And so the problem is how to construct non-trivial quasi-cocycles in degree at least 2, because recall that quasi-cocycles in degree n give exact bounded classes in degree n plus 1. Okay, so the main technique to construct non-trivial quasi-cocycles in degree 3, and as far as I know, basically the only technique which is known so far, is using volume forms. Okay, so what I'm going to describe today is a way to discretize volume forms in order to construct quasi-cocycles not from differential forms, but from something else. But in order to understand what is the philosophy behind this project, we start with differential forms and with classical volume forms. So we take an open pinch and negatively curved manifold. We take the universal covering, and we set G the fundamental group of M, which acts by isometries on the universal covering. And we are going to define a volume form. What is a volume form? It is the volume of synthesis, basically. It comes from the volume of synthesis. So first of all, for every m plus 1 tuple of elements in G, we want to define a straight simplex. Okay, so we fix a base point in the universal covering. We take the points in the orbit of this base point, defined by this m plus 1 tuple, and using non-positive curvature, which implies uniqueness of geodesics between points, we can construct what is called a straight simplex, something like a geodesic simplex with these vertices. Here, there are many ways to construct straight simplexes. There are methods using the barycenter method by Besson, Courtois, Gallot, but there is an easier way, which is sufficient to our purposes, which is just taking cones. So we start from these 4 points. We are going to construct a 3 simplex. So we take just the unique geodesic between the first 2 points. Then we cone from the third point using, again, geodesics. And this gives a face. And then we cone from the last vertex to the face, again using uniqueness of geodesics. And in the end, we end up with a parametrized, concrete, straight simplex in the universal covering. And then it's clear what is the volume cocycles. So when we have n+1 element of the group, we take the straight simplex associated to these elements in the way I've just described, and we take the volume. We just integrate the volume form. So this is a volume with sign, of course, because this can be positively or negatively oriented. A key fact is that if we have a pinch and negative curvature, then it can be proved that straight simplices have a uniformly bounded volume. Okay? Just like in hyperbolic space, there is a uniform upper bound on volume of simplices. And this just says that this cocycle is bounded. This is exactly the same. It is a cocycle just by Stokes. This is trivial. And it is bounded because we are in negative curvature. So it defines a bounded class. And in fact, it is an exact bounded class because we have an n form on an open n manifold. So this form is not only closed, but it is also exact. So this is in fact a class in the exact bounded cohomology of G, because we are working with open manifolds. Okay, if M were closed, this would be non-trivial also in the ordinary cohomology. Okay, it can also be seen that this class does not depend on the choice of base point, but this is not very important. What is much more important to us is the following question. When is this class non-trivial? So there is a conjecture by Grorov which says that this class is non-trivial if and only if the manifold is closed at infinity, which means that it has vanishing Shiger constant, which means again that we can take bigger and bigger submanifolds of the manifolds, such that submanifolds with boundary, compact submanifolds with boundaries, such that the volume of the boundary of these submanifolds divided by the volume of the submanifold is going to 0. Okay, this means closed at infinity because. Okay, I'm not giving a picture, but I can use my hands. Something is open at infinity if the geometric ends open up. And so also the volume of the boundary needs to be very big for every compact submanifold. If a manifold does not open up too much, then we can have vanishing Shiger constant, and thus conjecturally the volume form in this case is non-trivial. However, this conjecture is proven in some cases. For example, for hyperbolic three manifolds, this is known to hold. And this already gives a lot of examples because it is very easy to construct hyperbolic three manifolds with three fundamental groups which are closed at infinity. For those who are familiar with Thurston things, just take the cyclic covering of the figure 8 knot, for example. But I will give exactly a geometric description of why this is true for fiber manifolds. So this is just the general framework. I wanted to emphasize these things because there's still some work to be done here, and it seems an interesting question, this one by Gromov. In fact, as far as I remember, this is not a conjecture, it is a statement by Gromov. So he stated, so it should be true, but there is no proof written down anywhere. On the bad news side, there is this theorem by Lewis Bowen, which says that this method for constructing non-trivial classes stops in degree 3, at least for three groups, because in dimension, at least for an even dimension, there are no hyperbolic n manifolds with vanishing Shiger constant and three fundamental groups. So it's not easy to go farther with the dimension. So it's difficult to pursue this strategy in order to show the non-vanishing of the bounded cohomology of three groups in dimension bigger than 3. which is a very big open problem. Okay, so let us come back to what we know is true, and let us describe a very concrete example which tells why Gromov conjecture should be true. So we concentrate our attention on the case of hyperbolic three manifolds which fiber over a circle. So we take a pseudo-Anosov automorphism of a hyperbolic surface, and we construct the mapping torus as usual. So the fundamental group of the manifold is just the semi-direct product of the fundamental group of the surface times z, and we denote by T the stable letter of this semi-direct product. We are going to look at the geometry of the cyclic covering of this manifold. So the cyclic covering of this manifold is a regular covering, which is just homeomorphic to the surface times R. And how does the stable lecture act on this covering? It just translates the surface times by 1 on the right, and it acts by the pseudo-Anosov map we have fixed at the beginning. Okay, this is almost obvious. Okay, this is the action of the stable letter on this cyclic covering, and we get back, of course, our fiber manifold by taking the quotient of this cyclic covering by the action of T. Okay, now I'm going to prove that the volume form of this guy, okay, this guy is exactly what a closed at infinity hyperbolic manifold looks like, okay? Because here we have this periodicity, which means that we can construct big submanifolds which have fixed boundary, basically, okay? And this means that the Cheeger constant of this manifold is 0. Why does the volume form give a non-trivial bounded classes? So we take a straight fundamental cycle for a surface. So this one, we have a surface here. We take a straight fundamental cycle. Just think of a straight triangulation, for example, of this guy. And then we translate it by T to the end. And this gives another fundamental cycle for another fiber of this cyclic covering. Okay, the fiber which is obtained by translating this fiber on the right by n. Okay, of course these two cycles are homologous because they represent just the same homology class. So their difference is the boundary of something in the middle. Okay, and now there is a very easy computation which says that this something, this is a 3 chain. Okay, this is a singular chain of dimension 3, and it fills all this region. So it's very easy to check that if you evaluate the volume form on this Cn, then we obtain something which is comparable with the volume of this portion of the cyclic covering. So it is something which grows like n. Okay, the volume of this region here grows like n. On the other hand, if we suppose that omega is the coboundary of a singular chain, then we obtain that by evaluating omega on Cn, this is the same as evaluating the primitive of omega on the boundary of Cn. This is just the definition of boundary and coboundary. But now, what is the boundary of Cn? It's just the fixed fundamental cycle for the surface, its difference with the translated one. And so here we have an easy estimate. This is at most 2 times the L infinity norm of this cochain times the L1 norm of this chain. But this is just 2 copies. It is one chain, one fixed chain, and another chain which we obtained by translating the first one. So the L1 norm of this chain is just 2 times the L1 norm of the original chain Z. So here we obtain that this guy grows to infinity, while this guy is uniformly bounded by this quantity. So the only possibility is that the L infinity norm of B is infinity. B cannot be bounded, because if B were bounded, then we would have a contradiction. And this means that this volume form does not admit any bounded primitive. And this is exactly the same as being non-trivial in the bounded cohomology of this guy, which is equal to the bounded cohomology of the free group. Oh, I'm sorry. Here there is a mistake. Here is not the free group, it's the fundamental group of the surface, because the cyclic covering is homotopically equivalent just to the surface. Okay? So there is a mistake. We proved that the three-dimensional bounded cohomology, not of the free group, but of the fundamental group of a closed surface, is non-trivial. And the volume form gives a non-trivial element here. But the point is that you can play the same game by taking the mapped torus over a punctured surface, and this gives the same result also for free groups. Okay, so there's nothing strange here. And here we can also understand why this fact should be true for manifolds with vanishing Shiger constant. Because what you need here is exactly a big volume here, which is bounded by uniformly bounded n-1 submanifolds in the big manifold. So there is a, yes?
But so is omega bounded?
Excuse me?
Is omega a bounded class?
Yes, omega is bounded because here this guy, I forgot to say probably that this guy by Thurston hyperbolization, for example, okay, let me go back. This guy is hyperbolic. So any of its coverings have a curvature constant and equal to -1. So by what I said before, there is a uniform bound on the volume of straight simplices there. So the volume is bounded. So the volume class is bounded.
Okay, so bounded doesn't necessarily mean that it's like uniformly bounded on all chains. I mean, like omega of Cn is going.
Bounded means it's uniformly bounded on a single simplex. Of course, not on a chain. If you take 10 times, since it's linear.
Oh, sure, yeah.
Okay, on single simplices. Okay. Okay, now one can play this game in several ways, and the first who did this is Yoshida, who proved that different pseudo-Anosov maps give different volume classes, and so this guy is infinitely generated, basically. But then this result has been generalized to show that the dimension of the third bounded cohomology group, both of surface groups and of free groups, as the cardinality of the continuum. And but these proofs are just variation of the strategy I described. So in some sense, no new bounded class arises from these theorems. And some years ago, 2 years ago, we generalized this to acylindrically hyperbolic groups with Beatrice Pozzetti and Alessandro Sisto. I'm not going to speak about this theorem today, but let me describe the proof, because it will be the same strategy that I'm going to describe for the new theorem we have now. So the sketch of the proof is this one. So any acylindrically hyperbolic group contains a hyperbolically embedded subgroup isomorphic to the product of a free group and a finite group. Here, hyperbolically embedded subgroup is a non-trivial definition, but what is important, it has some convexity properties. So we can project the full group on cosects of the subgroup. We have coarse projections, but using these coarse projections, one can extend, this is the second step, one can extend quasi-cocycles on hyperbolically embedded subgroups to quasi-cocycles on the ambient group. So this is the content of our theorem, basically. It's this step 2, that quasi-cocycles from a hyperbolically embedded subgroup extend to the ambient group. And this just means that this restriction map is surjective, is the same. We have a class here, it's represented by a quasi-cocycle. If we can extend the quasi-cocycle to the full group, this just means that this restriction map is surjective. And then finite groups are not visible to bounded cohomology, and so we get finally this theorem by using Sommer's theorem. So we reduce this computation to this computation. This guy is at least as big as this guy, and this suffices to say that it is very big. Okay? Yes?
How could you use in 2015 a theorem from 2017?
I didn't hear any.
How could you use in 2015 a theorem from 2017?
Which theorem is in 2007? Oh, sorry, because this is when this paper was published, but this is where is Dennis? Okay, this is 2013 or something like that. I don't remember. Okay, so what I want to describe today is the zero-norm subspace. So remember that the L infinity seminorm is indeed a seminorm, probably. So we can define this space, which is the space of classes which have vanishing L infinity seminorm. And it is easy to check that this is contained in the space of exact bounded classes. So any class with vanishing norm must be exact. There is this theorem that in degree 2, non-trivial classes have positive L infinity norm. Okay? So bounded cohomology is Banach in degree 2. But things change in degree 3 because Sommer again proved that there are non-vanishing classes with the vanishing seminorm for the free group, and there are many if we go to surface subgroups. Here we already see that there is a small difference here because when you need to concretely give estimates, the geometry of puncture surfaces or fiber manifold with puncture fibers is a bit more complicated, and so here already there is this small difference in these two statements because the techniques that work here are it's very annoying to adapt the techniques that work here to the case of puncture surface. So at some point, Alessandro, Beatrice, and me, we had this theorem that did not take care of the seminorm, and we said, okay, we should just adapt our theorem to show that for acylindrically hyperbolic groups, also the space of classes with vanishing seminorm is huge. And this is what we did, in fact. This is our main theorem. We needed the help of Federico Franceschini because in order to prove things for acylindrically hyperbolic groups, you need to prove things for free groups because you want to extend quasi-cocycles from hyperbolically embedded subgroups, and you're sure there are free groups which are hyperbolically embedded in acylindrically hyperbolic groups, but of course you cannot ask for surface groups which are hyperbolically embedded there. And so we had to work on this. But the scheme of the proof is exactly the same. So we need first to prove the result for the free group, and then use the extension theorem. But there is a warning here that this map, which is surjective, may be distorted. So it is not even clear if the space of classes with vanishing seminorms here surjects onto the space of classes with vanishing seminorms here. So the point here, we want to prove that this is big, and this is one step, and then we want to use that there is an epimorphism here to say, okay, also this one is big. But there is a problem also for the second step of the proof, but this can be done in some way. More control is needed on class. We need to look very closely to our representatives of cocycles to show that even if this map could be distorted, we are able to construct classes here which are so controlled that we can find something here projecting to our classes which has basically the same semi-norm as the starting class. But this is not for free from our theorem from 2015. But I'm not giving any detail about this because the point is that I want to stress the fact that all the differential geometric problems that came from basically one needs to estimate the hyperbolic volume form in terms of the singular solve volume form and play with these differential forms in order to properly prove these theorems. And following a suggestion by Mladen Bestvina, we decided to forget about differential forms and pass to combinatorial volume forms, and things got easier. And so let me just describe how we did this. Okay, in order to avoid too many technicalities, we come back to the case of surface groups, but the same can be done for free groups. I will speak about Gromov hyperbolic groups. When you work with punctured surfaces, you need to replace Gromov hyperbolic groups with relatively hyperbolic groups. I will speak about Mineyev becombing. In the case of free groups, you will need not Mineyev becombing, which works for hyperbolic groups, but Groves and Manning becombing, which works for relatively hyperbolic groups. But everything can be adapted to the case of free groups. So we have an
relatively hyperbolic technology to deal with free groups?
Excuse me?
Did I mishear you, or did you just say that you need the relatively hyperbolic technology to do with free groups?
Yes. Yes. Right. Yeah. You need yeah.
You want to think of it as a cusp.
Yeah. You need yeah. And you need a becombing in that context, which is due to Groves and Manning. So we have a pseudo-Anosov automorphism of the fundamental group of the surface, and we have the usual semi-direct product. And now we know that by Thurston hyperbolization, this is the fundamental group of a hyperbolic three-manifold. So for sure it's Gromov hyperbolic. But I want to emphasize that one can do things without using hyperbolization, without using differential geometry. So one can use instead Bestvina-Fein combinational theorem to show that this is Gromov hyperbolic. Now we fix a Cayley graph x of gamma, and okay, now I need to define one chains, two chains, and three chains on this Cayley graph. So the Cayley graph is a graph, so we need something which is fat, not a graph. And what one usually does is constructing a Ripps complex over the graph. So this is a standard technique. We take the simplicial complex, which has a simplex with a set of vertices, if and only if every pair of vertices is close, say. Okay? Pairs of vertices in the simplex needs to be at distance at most key. And it is well known that since x is hyperbolic, then there exists a constant such as this guy, which is the Ripps complex over x, is contractible. So here we can fill chains. We can play the same game we played in the context of manifolds. Basically, we can fill chains. Every cycle is a boundary, and so on. This is needed for the estimates we're going to do. What is a homological becombing? It's just a way. You give me a pair of vertices in my graph, and I just need to connect them by a one chain. But I want it to be a simplicial chain in the Ripps complex. So I'm not allowed to take just the pair G0, G1, because if G0 and G1 are very far one from the other, there is not any simplex having them as endpoints in the Ripps complex. So we need to add simplices. But this, of course, can be done. And this is the picture. So this is one chain connecting G0 and G1. And when one can construct triangles and so on. Okay, a becoming has finite area if the all following holds. Okay, we take 3 vertices, we take the becoming of the boundary of these 3 simplex. It is just this one, okay? And then this is a cycle, so it can be filled in the Rips complex. If I can fill it with a simplicial to chain of uniformly bounded L1 norm, then I say that this becoming has finite area. This should mimic the fact that in hyperbolic space, geodesic triangles have uniformly bounded area. This should mimic this behavior. Okay, this is the picture, this is the becoming, and then I can fill it with the chain of bounded area. I want more. I want also that this becoming has finite 3-dimensional volume. Is the same thing. It has finite volume if once I'm given 4 points, I already know how to construct the faces by phi, and the union of the 2-dimensional finite area faces should bound a chain, a 3-dimensional chain of uniformly bounded L1 norm. Okay, this is exactly the same one in 1 dimension more. And the theorem by Mineyev is that since gamma is hyperbolic, gamma supports a finite volume becoming. Okay, this theorem should replace, in this coarse context, the fact that simplices in a hyperbolic 3 space have uniformly bounded volume. This is basically the same statement. And now basically we are done, because we can compute the bounded cohomology of the surface group just by looking at simplices with vertices on X. X is the Cayley graph of the fundamental group of the 3 manifold. So it is coarsely equivalent to hyperbolic 3 space, basically. So this plays the role of our universal covering of the manifold. And just this is an easy theorem. The action of gamma 0 on X is free. So this is trivial for all the experts in cohomology or bounded cohomology. In order to be true this, it should be sufficient that this action is amenable, but this is even free, so it's basically trivial. So now we look for non-trivial quasi-cocycles here on this space. So the space, this should be thought as invariant bounded cochains on the universal covering. Let me first define a projection of the universal covering to Z, which is just the universal covering is foliated by fibers, by the pre-images of the fibers, and this map theta is just the map which says, okay, I have a vertex which is in one fiber. I just take the power of the stable letter which is related to the point. Okay, I will give a picture. So points here have theta equal to 0. Points here have theta equal to 1. Points here have theta equal to 2. Okay. So what is the what do we need to construct? We need to construct a primitive of the volume form, right? Because we're looking for a quasi-cocycle whose differential should mimic the volume form. So we need to define what is the primitive of the volume form of a simplex like this one. What is the primitive of the volume form? By homotopy, it's the volume of this prism, basically. Because you have the 3-dimensional volume form is something here, and if you look for a primitive on a triangle, you have this homotopy, which shrinks all this guy to a surface, and you must take the volume of the prism along the homotopy. But here is a subtle geometric point. The point is that if the triangle is small, so if it is a simplex in the Rips complex, then this is basically true. If the triangle is small, we can just assume that the prism is what we need. And so we just take the average. Okay, this is our 0 time. If we are at time 2, we declare that every simplex in the Rips complex has area equal to 1. This is a normalization. And then this prism is just 1 times this length, which is basically the average of the theta coordinates of these points. It's a coarse definition of volume of this prism. This is very reasonable. But the point is, when delta is very big, then now a key fact is that these surfaces are very non-convex in this guy. So if you look at the small triangles, okay, you can just forget about this. But if you take triangles whose vertices are very far one from the other, then it may be that the geodesic, the becoming by Mineev goes here and there along the whole cyclic covering. So you cannot just compute the volume as we did for small triangles. So we need to fill, so we have this triangle, delta, we need to fill it with our phi, which is the filling of Mineev becoming, and this gives a picture which is much more similar to what should be the geodesic triangle bounded by the edges of this triangle. And then we can, so this is a chain, and every simplex in this chain now is small by definition, because this is a filling of the boundary of the triangle in the Rips complex. And then we can apply this formula to each single simplex here. And this gives the primitive of the volume form. Now we can just put everything together. We can twist this construction. This is exactly what happens if we take the volume form. We can multiply the volume form by any function. So for any Lipschitz map, we can twist this volume form by declaring that the volume of the prism is weighted by some function. And then it's very easy to check that this is indeed a quasi-cocycle, so its differential is bounded. This just because Mineev becoming as finite volume. This is a restatement of this fact. And the defect of this quasi-cocycle is very well controlled by the Lipschitz constant of the map we chose. And it is very easy to check that this gives a trivial class if and only if f is bounded. The case of the volume form is when f is the identity, okay? So f is unbounded. And by letting f vary, then we obtain the desired infinite dimensional subspace of that we were looking for. Just in the last minute, this basically finishes the proof, because we have constructed our discrete volume form. Let me just do a bit of propaganda of our, not maybe of the result is interesting, but I think that the techniques we developed are more interesting than the result itself. And why? First of all, because yeah, working with these guys, it's easy. So proving these statements is not difficult. It's not easy to construct things because I'm cheating a lot, of course, on all the estimates needed here to make the thing work. But then proving the statements is not difficult. While working with differential forms can be tricky. For example, as far as I know, it is not known when a top-dimensional form in a hyperbolic manifold with vanishing trigger constant admits a bounded primitive, for example. So this point here, characterizing exactly which differential forms give non-trivial bounded classes is not easy. And the second thing is that by having a control on all the constants involved, we proved this statement, which is just a particular case of a theorem by Brock, which estimates the concrete Riemannian volume of a fiber hyperbolic manifold in terms of the translation distance of the pseudo-Anosov with the Teichmuller metric. And how could we do this? Because the Riemannian volume is proportional to the simplicial volume. So we got an estimate of this type on the simplicial volume, because bounding the L infinity norm of a class from above is equal to bounding the simplicial volume of a manifold from below, and this is exactly what happens here. So we have a, let's say, almost self-contained and coarse geometric proof of this statement, which does not involve much the hyperbolic geometry behind this fiber manifold. And this is, okay, the statement is not that interesting because it is a special case of already known theorem, but maybe this sounds promising for the future, and that's it.
Thank you very much. Are there questions?
So maybe you said it earlier, is the cohomology or this bounded class that you get from your combinatorial volume the same as the one that you get from the hyperbolic volume?
Yeah, we didn't check, but I think it should be, yes. And I think it's also easy to check. Yes. Yes, I think so.
Are there any other directions in which you might want to sort of, I mean, now that you have this nice coarse setting, is there more sort of geometric group theory applications that you might want to? I mean, obviously
we hope so, but in some sense, the theorem of Bowen, a very nice thing would be to go from dimension from degree 3 to degree 4. But in some sense, that Bowen theorem says, okay, you should work for finding the right models. Okay, so we hope so, but we don't have any precise direction where to go now. That's the truth.
Okay, so if there are no more questions, thank Roberto again.